In this tutorial, we're going to show how to recreate the rollerball example from Unity with inside Omniverse. First, you make a new file. Go to File, Save As, and find the location. Here, we're saving it on the local nucleus server. Next, we're going to change the environment. By default, there's an environment sky. We can click on the environment tab at the bottom, go to the environment skies or a template, and you can drag them over to replace your sky. We can also delete the ground plane and start with our own ground plane. You can go to the Create tab, create a ground plane. We can scale it on the property attribute. If we don't like seeing the axis and grid, we can go to the eye icon and turn it off. We can also adjust other settings here, such as hiding the lights. Hiding the light is not turning off the light, it just changes the display. Let's rename our ground plane. And set it to have a new material. There are multiple ways to apply a material, and there are many materials to select from. When you first are trying to open up your material, materials have to download from the server. You can check on the bottom right, and there will be a download box. If you don't see it, you'll have to just wait a minute or two. Once we've created a material, we can change different attributes of it. There are multiple materials, and that would be a whole other section in a different tutorial. So we can drag and drop a material onto a plane. We can also select our object, and then once selected, we can use the drop-down attribute for the material and assign whatever is currently in our scene. We can also drag and drop from the material library on the bottom tab. Once you've replaced a material, you can go back to the object and switch between them in the property attribute menu. Next, we're going to add the ball to the scene. We can right-click and go to Create, Sphere, and Sphere. We can also move the transform by sliding it. And we want to create a physical scene, so we'll right-click and set our physics. You notice nothing happens because while our scene has physics, none of the objects in the scene are assigned to interact with the physics. So let's right-click on the ball, click on Physics, and add a rigid body collider in Physics. As you can see, the ball falls because of gravity. What we want to do is include the collider for the plane as well, so that the two objects will interact. Now that we've assigned the collider, both of them will fall. Naturally, both of them are interacting with gravity as well. We'll select the ground plane and find the physics attribute that enables kinematic. Kinematic enable means that it's going to be driven by an animation and not by physics. Now when we play, the ball does not fall through the plane and instead lands right on it. The Play tab will run everything at the same time, and we can modify the material of the ball. Another aspect of materials is physical-based materials. If you right-click, you can create a physics material. It'll ask you whether you want to make a deformable or rigid material. Once we've created the material, we can drag and drop to apply it. You'll notice that we lost our color of the material. The value of the physics material is that we can set things like coefficient of restitution and its mass. Now this material is changing the bounciness of the ball. We can, however, add both a physics material and the colored material to the object. We'll just have to go into the object's properties. Select your object, and find the Material tab, and now select the color of the ball. You'll notice later on, in the Physics tab, there remains the physics-based material. Next, let's create a behavior script that will run whenever the scene is run on the object that it's applied to. We'll right-click and specifically select Behavior Script to make a new behavior script. We can edit the behavior script by right-clicking and Edit Script. Depending on your configuration, this might open Notepad or VS Code. This comes with multiple preset functions that are automatically going to be called during the play loop. We can assign a script to an object. If we go to Add in Python script, it'll allow us to add an asset or add a script to that object, and we can select the script we want, or we can drag and drop the script onto that attribute. We can click on the Console tab, and if we run the script and enable on the Console tab the messages, we can see in blue the messages that are getting printed out. When we played it, all of the attributes from our script are starting to play, such as the ball game starting and the current position and delta time during the update loop. Because we don't want the overhead of continuously printing out during the update, we're going to select a couple functions and we're going to tell them to just return. Likewise, we want to make sure we know when our ball is falling, so let's just do a little edit and tell it hello. Another way to edit the script is under the script editor embedded inside of Omniverse. We can select our script and edit with inside the built-in editor. If you would like, you can also use VS Code. Here, we're opening the script inside of VS Code, and we're going to try to register our keyboard events. This means when we press a key, we want that key to be registered and perform an action inside our Omniverse scene. We're going to copy over a few imports that we've created before this tutorial. Importantly, we need to copy over the keyboard events. When we press play, we want to make sure that our keyboard events are registered. In this case, we are going to create some global scoped class variables like self._keyboard. And we're going to create a callback. Our callback is going to be called onInputEvent. And when that callback is called, we want to check which type of event it was. Here we will check if our event is correct and it's hitting the correct key. Then we're going to assign a different force value to it. Next, we want to know if the key was released. So when the key is released, we're going to change our value. Let's start with an initial force value of 0, 0, 0. Now when the first key is pressed, we'll assign the force to a different value. Each index we apply to the force is going to be the XYZ or force value. Really, we only want to apply the ground plane. Because the up axis is by default Y, we're going to apply the forces on X and Z. If your default value for your up axis was Z, you would apply the forces on X and Y. We need to create a force scalar, and we define how much force that is. Here we do something quite high, like 200,000, 20,000. We can change that later, depending on how fast we need the ball to move. One of the important things about behavior scripts and scripting in Omniverse is ensuring that when you create an event or a callback, you deregister and disconnect from that callback. Otherwise, when we stop running this script or we delete this script, these values still exist in the scope and will continue to print or cause problems in future scripts. The onDestroy function automatically will be called when the object is destroyed. We unregister the events. Likewise, when we stop, we want to call our onDestroy function. Stopping our play simulation is essentially like us trying to clear the entire game. Now let's check if our keyboard events were registered. We have our script, and we'll go to the console. When we press play, we should see the forces print when our key is pressed. So right now, I'll start pressing one of the keys, and we can see that the force is assigned and then unassigned. Great. So now our keyboard events are being registered. We want to use our keyboard events to then apply a force to the ball itself. We'll start with a few additional imports. One of them will be NumPy, so we can use NumPy for array creation. We also need some of the physics interfaces, both from the PixarUSD library and from Omniverse. Let's make our onUpdate function. This function, by default, will take in a delta time. On each update, we want to get the position of the ball. To do this, we will use the X-form of the prim, which is self.prim. That self.prim exists in the class scope because we've inherited the behavior script. We can then apply a world to local transformation, and we can extract the translation from that object. Next, we want to set the force onto the object. So we'll define a force that is given based on our force strengths on the keyboard input. To pass these objects to our physics scene, we need to convert them into carb values. So now we have a position as a float 3 and a force as a float 3. We're going to use the getPhysics interface and apply force at position function. All of our self.values come from our behavior script. So the code pieces are all there. We register our keyboard event, change the value, and assign that value as a force to the object at its current position. Now we can see that the ball rolls back and forth. And because the ground plane is the only physics that we have on the floor, the ball will roll off the floor. So let's create some walls to make sure that the ball stays within the game zone. We'll right-click and create another cube. We can move the cube with the internal gizmos, and we can use the shortcut keys to create the scale gizmo. This is an alternative to using the property attribute window. Let's rename our cube to a wall. And we can add our rigid body collider preset. Again, the wall will just fall over the ground, so we're going to need to add a kinematic attribute to it. One thing that you can do in the physics scene is hold Shift and use your left mouse button to click and drag the ball. This will let you move the ball around in the scene. Let's select our wall and duplicate it. Because our wall already has the rigid body attribute assigned to it, we'll be able to very quickly create all the walls for our scene. Now let's test out the walls by just throwing our ball around. We can modify the lighting of the sun by selecting our environment's distant light and rotating it. This rotation will remove the shadows from the environment. Similar to Unity, a game object in Omniverse is referred to as an X form. We can create an X form, which is like an empty game object, and create a hierarchy structure because of that. We'll create an X form called cubes, and we'll start creating our cubes inside that X form. We'll scale our cube down. Again, when we press play, our cube is not moving. And let's assign a nice shiny material to the cube. Now let's animate our cube. We'll first go to the Animation tab so we can see the animation timeline. The animation timeline will become useful here because our kinematic-enabled rigid bodies will not move based on physics, but they will move based on a driven animation. Let's find an offset rotation that we can start our cube's animation from. Like in most cases, animation is done with setting keys to specific attributes. We can right-click on each part of the transform and set the key, move our timeline further down, and then set the key of our new rotation. You'll notice that a key is set when there's a red attribute. We can also right-click on the rotate for all three axes and set the key for all of them at the same time. So we can see by dragging our ball that although the cube is in the scene rotating, it doesn't have any kinematic attribute or physics attribute assigned to it. We'll right-click the cube and we'll add a rigid body with collider attribute. Now the ball will just fall and doesn't play any animation. So let's make sure that kinematic is enabled. Now let's make sure that the ball won't go through our cube. So we can drag the ball and it'll hit the cube. The cube will continue to spin. Let's repeat the same process that we used for our player ball by right-clicking and creating a new behavior script for the cube. Again, we go to the Add property and add a script. We drag over the cube script onto the Python script of the cube. We'll rename the cube 01 so that when we duplicate the cubes, we'll have a good naming convention. Because all of these cubes are inside of the cube X form, we'll be able to reference the entire set later in the script. Now that we've moved our cubes around and animated all of them, we can move our ball just to check that each cube has a rigid body collider and maintains its rotation. In order to register that our cube has collided with something, we're going to open up the behavior script, delete a few things that we don't need right now, and then start registering some physics. When we had set our object to have a rigid body collider, we can now use that collider to recognize when the object has hit something. When we press play, we want to set a collision attribute, and that collision attribute should be enabled. This means that every time we press play, the physics of the ball should be set to enable collisions. We also have to define a collision threshold, and we'll create a callback that we're calling contact report sub, which really stands for subscriber. We have this on contact report event. So let's make a function for the on contact report event. This event will take in contact headers and the contact data. Finally, we need to apply the collision API and the contact API to our prim. Like before, on the destroy, we need to make sure that our collision attributes are set. We also need to make sure that we unsubscribe from any events that we've registered callbacks to. It can also sometimes be good practice to set your callback to none just to make sure that it's been deregistered. Similarly, on stop, we want to call the onDestroy function. Now let's edit our onContact report event. Because this event is not specific to this cube, we've instead just registered to all contact events. We're going to iterate through all events of that contact within this single frame. Each contact event will have two colliders, collider 1 and 2, and we will get them through actor 1 and 2. Let's set a list of colliders so we can check whether our object is within that list. Using our prim path that we've inherited from the behavior script, we can check if our path is within the contacts list. We can then get our collision attribute and set it to false. Let's make sure that our cube script is attached. Now when we press play, the initial ball collision will show a slight collision and then go through the ball. So we'll see the ball collides, and after the first collision, there is no collision set for that cube. We can also notice that each cube was individual, so the behavior script attached on each individual cube has its own prim path. Now we're going to set our visibility. We want to be able to turn off the visibility of the cube at the same time that we turn off the collision. Each object has an attribute called visibility. So we'll go back to the code to add a visibility attribute that we can turn on and off. So on our prim, we'll get the attribute visibility, and we'll make sure to turn it on when we destroy our object. The code is almost identical to the collision. The only difference is that we need to add, inside of our contact reporter, a visibility toggle. So when we play, we will get the attribute of our visibility. We'll set it to visible. And we'll make sure when we destroy, it is also set to visible. In the same way that we select our collision attribute to false, we can set our visibility attribute at the same time. Now let's test and run the code. While we move the ball into a cube, it not only turns off the collision, but turns off the visibility of that cube. Now let's go to our player, the sphere, script. Similar to the ball collision, we want to register our player's collision. Again, we're going to create a contact report callback, setting our collision threshold, and creating an onContact event reporter. So let's make our function onContact report event, take in the contact headers and the contact data. Again, we're going to iterate through all of the contacts that had just happened. This time, we want to know that the contact was lost. And let's check if our player is within the contact set. So now that we're printing that the player contact has ended, what you'll notice is even when we hit another object, like the floor or the wall, it also registers as a contact. In order for us to record a valid score, we want to make sure that the collision is not just within the player itself, but also with the cube. We set our cubes into a group, and using that group, we can traverse the cubes to make sure that we know all of the cube path names. Later, during the collision, we're going to check whether our sphere player has collided with any of the cubes that we've decided are going to be things that you can score points with. We also made a new score attribute. As the prim does not have a default attribute called score, it'll be hard later to register that score and use for a heads-up display. So we create one within the startup. Rather than just printing that the collision ends, we're going to add a 1 to our current player score. Likewise, we're going to set our score attribute to the player score. Now, every time we move the ball, we have an increase in score during the collision. However, our collision is going to register for everything, so we will use the cubes. First, we'll get the cube path, which is world/cubes, and we can see the prim path in the property attribute. That empty X form contains the 4 cubes that we want to register. Since we have the path, we want to get the prim at that current path and we'll refer to it as the parent prim. This is the empty game object. We'll check if that prim is valid, and then we will traverse all of the children. We can make a list of all of the cube prims and assign it to our self.cubes. During the contact report, we now want to check if our cubes are inside of the collision. So let's make sure that collider 1 or 2 is going to be the player object, and the other collider is going to be one of the cubes. This will prevent the score from happening whenever we hit a wall or a ground plane. Now let's play and see if it works. We don't get any score when we hit the ground, and if we start using the key presses, we can notice scores only when we hit the cubes. At this point, we're registering scores and moving around the ball with our keyboard. We've created animated cubes that have rigid body colliders on them, but do not act with physics or gravity, only with the collisions. We're going to clean up our environment a little bit to make a nicer game board.